Hey there, chemists. In this lesson, we're going to look at a new reaction that makes rings. This is called an annulation, which is already written there on your notes over on the left. And an annulation means a ring-forming reaction. This was developed by Robert Robinson, who was a British chemist, Nobel Prize-winning British chemist, and you can see where parts of this 4-carbon enone become this part of the 6-membered ring, and then here we have another ketone and it becomes those carbons. So you actually make 2 new carbon-carbon bonds in this reaction. This bond is formed by a conjugate addition, and this one up here is from our most recent reaction, the aldol. And what happens is they happen in tandem. This is a tandem reaction, meaning back-to-back. So let's look at an example and see if we can walk through the mechanism of how this happens. Here's an example using cyclohexanone and butenone. So it's always some kind of ketone with an enone and base. Those are the conditions of the reaction, usually thermal. And you'll see that that drives that condensation that we saw when we learned about the aldol. So we're in base. The first thing that's going to happen is generating an anion. To do that, I'm going to just redraw cyclohexanone. And hydroxide will act as a base. It's going to take away one of those alpha hydrogens and make an enolate. Remember, you could just draw the enolate as an alpha anion right next to the carbonyl carbon, so you get an enolate. That's almost always the first step in any of the mechanisms in this unit. Now, we've seen enolates do many things. We saw them do aldol reactions where they attack carbonyls. We saw them do SN2 reactions where they attack alkyl halides. Enolates also do conjugate addition reactions, and that's what's new today. This is going to set us up to do a conjugate addition. Just like cuprates can react in a conjugate sense, enolates can do this too. So they don't attack the carbonyl when there's an alpha-beta unsaturation. They end up attacking the beta carbon. I'm going to keep track of my carbons. I have my cyclohexanone, and then I have 4 new carbons attached at the alpha position. 1, 2, 3, 4. There's a ketone 1 away from the end. And then my arrows show me that there's going to be a new anion right next to the ketone closer to the ring. So I have an anion right there. In fact, that's just another enolate, isn't it? That's how conjugate additions work. You've been seeing enolates this whole time, anytime you do a conjugate addition. This, just like any other conjugate addition, will pick up an H from some acidic source. We have water in this case, so I'll protonate the enolate. Whoop, 1 too many carbons. And then I get a neutral diketone. So that right there is the conjugate addition part. You form the enolate, it attacks the enone, and it protonates, and you get your intermediate. But we're not done. This keeps going, and we're set up to do an aldol condensation. Our most recent reaction was how to make alpha-beta unsaturated carbonyls, and that's making this bond via an aldol. And remember, aldols come from one carbonyl combining with another carbonyl to get to an enone, and we use the ostrich rule to sort of figure out the products of those. So let's do that here, and let's see if we can figure out where we form the enolate and where it attacks. When remember you have multiple ketones like this, there's multiple possible enolates you could form. We could form an enolate right here, all the way on the end. And if we do, and imagine an aldol, it would cyclize to that carbon. That would give us a 1, 2, 3, 4, 5, 6-membered ring. That's good. We could alternatively form an enolate on the other side of that same ketone, and it could cyclize with the ketone, but that would give us a 1, 2, 3, 4-membered ring. No good. We could form an enolate here on the more substituted spot. That would cyclize with the other ketone, also giving us only a 4-membered ring. No good. And lastly, there's a possible enolate we could get up there, which could cyclize with the other ketone, giving us a 6-membered ring, and that is a good ring size. Due to the fact that this bond formation is probably more strained, and the fact that I can tell from looking at the product that it's not that type of bond forming, we're instead going to form an enolate right there. So let's draw in one of those alpha hydrogens and use another equivalent of hydroxide to make that enolate. Everything in this step is exactly the same. We just have a negative charge all the way on the end here. So all we did was go from one enolate to another. And now we're going to go forward with the aldol. How does this work? It cyclizes. That alpha carbon will form a bond with the other carbonyl. This is the beginning of an aldol addition. So that carbon now has an oxygen anion on it and a whole 6-membered ring. And we still have this ketone. It's not doing anything other than stabilizing that enolate. Keep track of where it is. It's not right there next to the fused ring. It's one more away. So there I put it. You can also sort of cheat a little bit and look at the product and realize it's going to start to turn into that. Now we just have to finish up the aldol. Thinking back to our most recent lesson, that oxygen anion picks up an H. So you get your aldol addition product. And remember, for ketone-ketone aldols, which this is, the addition product is not stable. It will thermodynamically either reverse or, in this case, continue to go forward and form the condensation product. That happens by forming yet another enolate. So the anion takes away that H, the CH bond breaks, you get another negative charge right there. Lots of the molecule just along for the ride. And we're almost done. To get to the condensation product, that enolate kicks out the hydroxide. That's why this works. It's the formation of that stable negative charge because it's an enolate that drives that hydroxide to leave, and you get a nice thermodynamically stable cyclic product. So it's a lengthy mechanism, but all it is two reactions we already know back to back. There's the conjugate addition, and then here is the aldol condensation. In fact, I'll go ahead and highlight that. There's the aldol condensation, and here was the conjugate addition. And that's the Robinson. That's how it works. So let's practice. Let's see if we can use it and also figure out a Robinson starting material, kind of like what we did yesterday with the aldol reaction. Here is a Robinson product. A Robinson product is always going to be a 6-membered enone. It's always going to be that case, and you're going to have a minimum of a 4-carbon piece that came from, or actually it'd be this 4-carbon piece, that came from the enone and then something else that used to be a carbonyl. I can see where this molecule ended up. It's this part right here. So there's all the carbons. So that means if I figure out what the missing product is, it's got to be the part that adds up to these 4 carbons right there. Those are the parts that are missing. So let's figure out what that would look like. I'm going to get rid of that question mark right there. And in its place, we'll just draw what I would have. It would be exactly this, but with an enone. I'd have an unsaturated carbon-carbon bond between the alpha and the beta position. And we could have figured that out because, remember, you can go backwards. Where did this come from? Thinking to what you know about the aldol part, just take that trick. Break the alpha-beta bond, draw what it used to be with that bond not there. The alpha carbon, fill in with H's, done. The beta carbon, what becomes the beta carbon? Make it a carbonyl. And then going backwards from this, what did the conjugate addition look like to get us to there? The conjugate addition also makes an alpha-beta bond, but it's alpha and beta to the other ketone. Lots of alpha-beta bonds that we're going to talk about in this unit. And that would look like the starting diketone that they're actually giving us, and then this piece where that used to be an alkene right there. And there we go, which is exactly what we just drew a second ago. You might be wondering, like, what's up with these reagents right here? This is just a Lewis acid. And it drives the reaction. Really all you need to know is look out for base for our purposes and heat to go to the condensation product. That's how you're going to get to a Robinson annulation product, starting with an enone and at least one ketone in your starting material. Remember, these diketones are great because that alpha hydrogen that's flanked by both gives you a very stable anion surrounded by ketones because it can resonate into one or the other. So it's a much better starting material than just a simple, let's say, cyclohexanone molecule. All right, let's close this lesson up with some syntheses. We're using some aldol chemistry here, actually looking at the products. Neither of these look like Robinson products because they're not six-membered enones. A Robinson always makes a six-membered enone. We have enones, but they're not six-membered. So these are just straight-up aldol products. So let's do a retrosynthesis and think backwards. If I see an alpha-beta unsaturated carbonyl, I'm thinking aldol. So I can imagine forming that alpha-beta bond, fill in the alpha with hydrogens, the beta make it a carbonyl, in this case an aldehyde. How do I get to this from this starting material? Well, that's an ester. We got to open up that ester bond. So I'm actually going to go forward with this. One of the best ways to open up an ester bond is lithium aluminum hydride. That will cut right through that carbon-oxygen bond. You'll get every carbon that you started with, but each oxygen becomes an alcohol. So I get this as a diol, which I'm just going to redraw. Let's unfold that. Looks like I have a 5-membered ring and then a 1, 2, 3, 4 carbon chain attached. So I'm going to redraw that as a 5-carbon ring. Happens to have a primary alcohol on it. And then it looks like 1, 2 carbons away, I have a 4-carbon chain. 1, 2, 3, 4, and then there's a primary alcohol in it. And you can see why I redrew it, because it's very similar looking to the intermediate that we want to make. Hopefully you can tell, this is just Orgo 1 chemistry. How do I get from that diol to make it an aldehyde and a ketone? Do a Sworn oxidation, or PCC, or PDC, or any other mild oxidation that we've seen. There you go, 3 steps. I'll just replace the word aldol with actual reagents. Let's use hydroxide, water, and heat. You just need base and heat. So 3 steps. So, before we stop, I'd like you to hit pause and see if you could do the last synthesis on your own. Notice it also has an enone, an aldol product, and we have a ketal from a couple of units ago. Go backwards and see if you can figure out where this enone came from using an aldol reaction, and then what you could do to the starting material to get there. Okay, let's take a look. So going backwards, I'm going to draw what this product used to be prior to an aldol. If I do that, that alpha-beta carbon bond was formed from that aldehyde and that ketone. And then I look at this and I see I have a ketal, which I can make from a ketone. And then I have an aldehyde and a ketone, which, oh, I have an alkene. So I think I can make those 2 carbonyls all at once from this alkene. And then somewhere along the way I also have to turn this ketone into a ketal. Now I'm already thinking about what to do in the forward direction. I think we got to protect that ketone first as a ketal, so ethylene glycol and H+. Will give us the ketal. And then how do I get those two carbonyls in one step? You can do an ozonolysis reaction. Step 1, ozone, and then some reducing agent like triphenylphosphine, dimethyl sulfide, or zinc, any of those. And that actually will cut that bond right there. You'll get an aldehyde and a ketone. And now I can tell, why didn't I wait to do the ketalization step? Well, imagine if you ozonized first. If you do ozone first, you're going to have a ketone, an aldehyde, and another ketone, and try to selectively protect just that ketone. That's going to be really tough to do. So get that ketone trapped as a ketal first, and then you can work with these two carbonyls and do an aldol. I'll just fill in my aldol reagents, hydroxide, water, and heat. And we're done. So another 3-stepper, just a little bit bigger molecules than we're used to seeing, but all using some new chemistry. Okay, so that's how we can use the aldol in some synthesis examples, and also how we can put it after a conjugate addition to get what's called a Robinson annulation.